Good morning, everybody. Sure. Okay. Sorry, I got other things going on here. So let me get my things set up. Yeah. So I encourage you all to click on the Magnus participants thing and open up the chat. Good morning. I also would encourage everybody to turn on their video if they're willing. I'd love to see your faces. If you don't, that's fine. What I would really also appreciate, if you don't want to have video up in general, is having a picture that is something other than just your name. A picture of yourself is great. A picture of something else that you like flowers or something, just to make it a little more colorful up there. Also, Francesca is still loving your picture. That's great. Yes. But yeah, some picture would be awesome. Don't have to get it right now, but for the next class, I would like that, just so I can see who everybody is. I don't know a lot of you because you haven't been in my math class. I mean, some of you I do, but some of you I do not. So I can kind of scroll through your faces. Also, I need to pin myself here. Let's pin myself there. I pinned my video, so it's big. You can all see my Calc 2 stuff in the background for now before I erase it. Let's see what's going on. Should have had one of these. I'm gonna have a Ricola before we get going here. As we get going here, which I'm sure is gonna sound great when I talk with it. I should have eaten it before, but trying to help my throat out here. That sounds terrible. Nope, sorry. Changed my mind already. I can't talk with this in my mouth. That was lovely. You all appreciated that. Okay, so couple things. So I figured out, I don't know if any of you have tried to look at the quiz that's coming up on Monday, which I haven't written yet, and I'm not sure what will be on exactly. But if you tried to look at it, you couldn't open the PDF in Gradescope because that's not how Gradescope works. So I've changed around the quiz now. In fact, actually, let me show you all. So let's go to the right place here. Let's close that. Let's minimize that. So if you want, I'm going to share my screen. Yeah, that screen. Share it. So if you look here, I am in the people part, which you can't actually see. In fact, those three of you, Nicholas, Victoria, and Joyce, if you could let me know whose class you're in at some point, either by a private chat right now or later on, that'd be great. But if you look at the assignments section of Canvas, and if you look at quiz 1, sure, quiz 1, a second I edited it, yeah. So if you look at quiz 1, now at the top, you'll see a link to the Stats 13 quiz 1, which if you click on it, will download something of them. And it says, this is a placeholder quiz, no idea what I'm going to do for it. But that'll be, eventually we'll actually have a quiz on it. And then the idea for the quiz on Monday will be that there will be stuff there. There'll be problems for you to do. If you happen to have a printer, you can print it out and write on it. If you don't, you can just write on a blank piece of paper, and then you can upload your answers to the quiz. I would recommend, if you don't have a scanner, which has a scanner, I mean, people have scanners, but I don't have a scanner. I would recommend using one of the apps that I think you guys were actually telling me about. I have found Genius Scan to be the easiest for me to use personally. But whatever you want to use, they make a nice looking document when you upload it, as opposed to just taking a picture with your phone. So do try and use one of those apps to scan your quiz in. Again, as a reminder, everyone who does the quiz will get all the points, and then they'll also be able to give you some feedback on how you're understanding the material. So let's see here. I think I can stop sharing my screen. Okay. Couple other things I wanted to mention. So I saw that for those of you in Nimdari's class, where'd you go? Oh, that's the thing I closed. I meant to keep open. For those of you in Nimdari's class, he has posted some homework with solutions. Still worth doing, but it seems, I feel like I might have waited to post the solutions a little bit before and give people a chance to do the homework about them. For those of you in Whitener's class, I've been looking at the textbook, and it's a pretty good book, I think. If you you click through the pages as you read along, and then every once in a while there's kind of little things like, for example, I'm going to share my screen again. I know I said it's done, but here we go. So I was looking through the textbook and doing the things, and so here I'm on the page about measures of center, comparing the median and the mean, and they're giving you some data sets here with numbers here 64 through 73, and here 64 through 730. Clearly, the point of this problem is that 730 is probably an accidental entry or some weird outlier. And so then they talk about how the mean or the average is very sensitive to outliers, right? If you have something big like this, it's going to make the average a lot higher than it really should be. In fact, they talk about how for the second data set B here, the mean is 162, whereas for the first data set, the mean is 68.1. Both data sets have a median, which is just the middle number of the data set, of 68. Right there and right there. And they talk about how if you have an odd amount of data, it's exactly the middle number. If it's an even amount of data points, then you average the two middle ones to get the mean, or sorry, the median. So the median is not really affected so much by outliers. The mean definitely is. And so then you read some more stuff. This is skewed. I'd say this is skewed right. Yeah, so this is a skewed right distribution. The mean, which we often write as X bar, is bigger than the median when it's skewed right. Because if you skew it, if you skew it right, I'm going to the right when I do that. I see some, is this the right for you guys? Yes, no, yes, okay, great. I always have so if it's skewed to the right, it means those big outliers up there are going to be making your average a lot larger while keeping your median still about the same, because the median is just the middle number. Whereas if they're skewed left that way, it means those outliers in that direction, or that data that's way down the tail there, is pulling your mean down below the median. An excellent example of this is when the people talk about the median income in the United States versus the mean income. The average or mean income is really, really high because there's some outliers like Jeff Bezos who make millions and millions or billions of dollars. And when you average those into the regular population, it makes the average income really, really high. Whereas the median income, which is just the middle number, meaning half the people earn below that number and half the people earn above that number, is a much better measure of the middle amount of income in America and the world in general, because you don't get this skewing effect of really, really high incomes or really, really low incomes. But the point I was trying to get to here is that after you've read all this, then there's some questions that ask you to answer. And they're pretty, I think they really do a good job of getting to the point of what you're trying to understand. So if you're in Whitener's class, I think actually reading through the textbook is useful and valid, and definitely trying to answer the questions is a good measure of your understanding. So I would recommend doing that. And then also, if you're in Whitener's class, once you get past that point, then you have to do, I think I already did the quiz, so it's not showing the quiz, or maybe I have to click on the quiz. But yeah, so if you click down here, then there's a quiz. So before she changed the grading, I had like a 92% because I did it one time and I got like an 85 because I missed the question. And then the second time I did, I got 100. But I think she changed her grading scheme, so now it's just whatever your highest quiz score is, so you can repeat it a few times. But the questions are somewhat different each time you do it, so just be aware of that. But I would definitely recommend trying to do the quiz until you get 100% on it. So I think that's all I really wanted to say there. Oh, I guess, actually, let me go here real quick. Sorry, where is my files? Come on, files. Spring, we don't need that. We want this. So I'm not in touch with him, Dari. He hasn't been very responsive to my emails, but one of the students, I don't remember who at the moment, but I appreciate you sending me the stuff. If the person who has been sending me stuff for him keeps sending me, not everyone else, that'd be great. But he posted a homework. I don't know why I'm trying to show it to you because you all should just have it. So let's not worry about that. Okay. All right, back to regular, all me, not my computer. So that said, I feel like this class is more difficult to come up with questions for right now because we're kind of at the very early stage of just like, how do we talk about statistics, right? I mean, there are some numerical examples where we have to calculate some things, but a lot of the questions are just kind of like, what does this mean? So I guess I should, and I'm probably gonna start off this way, most classes. Is there anything you guys would like me to talk about right now? Are there specific words or definitions or mathematical things that I could expand upon? I'm going to give you guys a minute to think about that. In fact, I'm going to use the restroom while you think about that because I really should have done that before class started. So think about it if you have any questions, and I'll be right back. All right, sorry, I had to wash my hands for a minute. So, anybody have any questions?
I have a question.
Great.
Can you go over the levels of measurement or the scales of measurement?
Levels of measurement. Yeah, I
can. Whitener talked about them yesterday, like the nominal, ordinal, interval, and ratio.
Totally. Yes. Yeah. That's what I thought it was. I had to make sure. So, and I think she's using levels or scales interchangeably there, right?
Yeah.
Okay. So, yeah. I don't know if I actually need to write on the board for this, but it's good to have a blank board. So there are 4 levels or scales of measurement. I feel like scales is maybe a better word, or whatever. So, right board. Actually, I have just a little bit more space over here. Yeah. So there are 4 scales of measurement. And the first one is nominal. Basically, I think she also says this. Yeah, well, and I think that's what we get to that, Francesca. Nominal is basically categorical, meaning a good example that she used was, male or female, right? Like you're trying to respondents, or blood type is also a good nominal category. So some examples of this are sex, blood type, whether you test positive or negative. So often in this class, they talk about HIV testing. So if you're HIV positive versus negative, these are all examples of nominal scale, nominal measurements, right? We're just trying to basically separate people into different categories. I think there's also, there's an Excel file she has you download, the friends file, where people say like, all right, is it easier to be friends with the opposite sex versus the same sex? And that's definitely a nominal category as well, right? There's no measurement there other than just saying I'm this thing or this thing or this thing. The second type is ordinal, I believe. Yeah, ordinal. Meaning it's categorical and it's ranked as well. Yeah, totally. We'll get to that. That definitely gets to when we talk about the interval and the ratio one. So yeah, we'll get to the zero non-existing thing in a minute. So an ordinal one, I think she gave the example of like your letter grade, right? Where it's still categorical, meaning A, B, C, D, or F. She didn't say F, which I thought was funny. But there's a ranking, meaning one is definitely higher than the other. And now I'm trying to think of some other examples of ranked things that are not just numbers. Certainly, I mean, I feel like you could say that placement in a contest. Like that would kind of be another, like you have it first, second, and third place. That's kind of an example. I feel like that might not be. No, that's a bad example. I'm going to take that one back because you can only have one first place, one second place, etc. How about like if you? So this is going to be kind of a funny example, I think. If you made some jam and entered it in the state fair, right? You get a blue ribbon or a red ribbon or a white ribbon. Ribbons at a fair, right? They're definitely nominal, meaning you're blue, red, or white, but there is a ranking. And the next one, which she said, and I kind of agree, is the interval one. Interval. So this is quantitative, so meaning numerical. And this is the one that doesn't have a natural zero as a starting place. So a very typical example which she used is temperature. Now, there is a zero temperature depending on either scale, right? There's 0 degrees Fahrenheit, 0 degrees Celsius, 0 degrees Kelvin, which is absolute zero. Someone maybe could argue that the Kelvin scale has a natural zero. But with temperature, although there is a 0 degrees Celsius, that doesn't mean there is zero amount of temperature. So when you're talking about an interval thing like this, if zero doesn't mean you have zero of the thing, then that means it's this type of interval. There's also, what's the other thing I want to say? There is, Yeah. You can take differences. So you can say like the difference between the temperature today and the temperature tomorrow is 10 degrees cooler. But again, that doesn't have a lot of substantive meaning when you say, right, like what does 1 degree really mean? And the problem with this interval example as well is, at least to me, it's hard to think of a lot of good examples. Does anyone else have an example of something that is an interval measurement that doesn't have a natural zero? I feel like she gave another one in her lecture, but I don't remember what it was. It's okay if you don't. I just. Yeah. What about?
I have a question.
Sure.
Oh, actually, I guess not. I was going to say, can age be thought of as an interval, but I guess that wouldn't qualify as an interval because it's not quantitative.
Well, I think it is quantitative. Like you could say, right, because the age is the number of days or number of years.
Yeah. Because you don't ever start out as zero. Like you're never 0 days or 0 years old, really.
I would maybe disagree. I would say at the moment of birth, you are 0.
Okay.
But okay. Yeah. So I think actually age would be in the next category, which is a ratio. So age, I think actually would be an example of that because there is a meaningful 0, and having 0 age is when you are, right, you don't exist. You have no years until you're right there, you're born. We won't talk about moment of conception, right? We'll just say whatever. Amount of money is an example she gave. And I feel like there are lots of, I mean, basically if you're counting something, usually ratio is a good example. So for example, like number of people with a certain characteristic, that would definitely be ratio because right, if there's 0 of them, then you have 0 of the thing. Yeah. I also was right for interval. I was writing down altitude. I feel like what the altitude someone is at could be an example of an interval because there really isn't a natural 0. You might want to say like, what's the word I'm looking for? Sea level is a natural 0, but it doesn't mean you have. Do you have 0 altitude at sea level? I don't know. So again, this one is the hard one. I feel like we'll try not to get too caught up with that. Yeah, I can really maybe heat add motion, sure. So these are the 4 scales of measurement. And we kind of know, I feel like we definitely use nominal scales of measurement a lot. We probably use ordinal less. We definitely use the ratio ones all the time when you're talking about a lot of different things, which we will get to. So is there anything you'd like me to clarify here? Okay. I know. So Francesca asked, when we use a stem and leaf plot versus a histogram when looking at data, or what's the difference? Okay. So to me, a stem and leaf plot kind of actually is like a histogram. And I feel like she actually gave a good example. Sorry, was the word in the last section? Let's take a look here. Ribbons at a fair. So like a state fair, you might get a ribbon for entering into some sort of competition. You get a blue, red, or white ribbon, and blue is better than red, and red is better than white. So it's still nominal, but there is a ranking of sorts, which is what ordinal means. Okay, so histogram versus. So I will say blanket statement here. One of the challenges of talking about statistics is coming up with examples. You often need a semi-large data set to make things at least seem reasonably interesting, which is hard to just create. So I'm going to go ahead and look back at her thing for 1 second. That's not what I wanted. Sorry, come back here. So I am looking at her book. I don't want you. Apologies. And if we look back here for a second. Yeah. Oh, actually, great. I'm on the page. So I'm going to share my screen again. 1 second here. Yeah, I've got 2 screens. Okay, come on. So if we look here, I think this is what I wanted to do. So she's got this example of ages of best actress Oscar winners, and this other example as well. If we scroll down here, you go ahead. Okay. So here is a stem and leaf plot of those ages. So if you look at this here, we're looking right over here. Oh, can I do that? That's cool. Cool. So I want just this. So we look at just this for a second. I can make it big. All right. So the way you read this is the ages are 21, 22, 25, 26, 27, 28, right? All those. So this is the first digit of the data. This is and these are all the second digits. So the nice thing about a stem and leaf plot is that it preserves all the data for you, right? You can still look at this plot and see all of the ages of the various actresses that have won the best Oscar, which is cool. Now, where did you go? Sorry, it's hard to see the things I want to see. Thought it was, no, I guess, okay. Let me go back. Let's go back to page 27. No. Stem plot. So Variance, so that's what we've got right here. Now, if you look at this other screen here on the left, you can see that this is a dot plot of all the information, which is not, I don't think, particularly helpful, right? It doesn't, it kind of, I feel like, moves the data out too far. If you look back up here at this stem and leaf plot, which has been turned on its side, it looks a lot like a histogram, right? It kind of shows you a lot of the ages. And usually these stem and leaf plots are broken up into 0 through 4 for the second digit, and then 5 through 9 for the second digit. So you've got this first bar here is 20 through 24. And the second bar here is 25 through 29. And then this is 30 through 34. This is 35 through 39, et cetera, et cetera, et cetera. Whereas, come on, you can look at a histogram. So a histogram gives the same sort of information as the stem and leaf plot, right? Like we can see if the stem and leaf plot is turned on its side, it's got that same kind of info, but it might be broken up differently, right? Like this one, which is not the same information, but you have intervals that are the whole 40 to 50, 50 to 60, 60 to 70. In fact, we can bring this here too. Yeah, I kind of like this. It's kind of cool. So, right, we've got that. So this doesn't preserve the information exactly, right? I don't know. I know there's one person who's aged between 40 and 50. I'm pretending like these are ages, but I don't know what age they are. I know there's 2 between 50 and 60. I know there's 4 between 60 and 70, but it doesn't actually tell me what the ages are. But it still gives me a broad kind of look at the shape of the data. I want to see if there's another one down here. Oh yeah, cool. So, oh, come on, give me the graph. Of course, it doesn't give me the one graph I wanted to give me. Hopefully, let me load this page. Yeah, there we go. So here is the look at the best actress data as a histogram, right? So they've broken the ages up into category age 17 to 22, and then 23 to 28, and then 29 to 34. So they're not, I don't think, particularly natural age breaks. Like I would have picked something more like 15 to 25 and 25 to 35 and 35 to 45. Those seem like in our base 10 system what we are more likely to pick, but it still kind of shows the same information. So hopefully that kind of addresses your question, Francesca. What else should we talk about? I have a couple ideas. I guess I kind of do, but not a lot. I feel like we're still young in this class. A couple things. So let's talk about median mode. Because these are things that will definitely come up over and over again. So the mode. So the mode of a data set is the piece of data that occurs the most. So the thing that occurs the most. And for example, if you were talking about, say, I don't know, what's a good example? The height of men in the US. The graph of that would probably look something like this. And I'm not going to, so you could draw a bunch of little things like this. Right? Maybe this is like let's say like this is like between 5, 9.5. That's a terrible way of writing this. Not 5.9, it's actually literally 5 feet, 9.5 inches to 5 feet, 10.5 inches. Let's pretend that's this highest bar here, and then other heights that have less and less people that are those heights as you either get much taller or much shorter. So looking at the way I've drawn this, I would say that the mode is exactly, I'm going to call it 5'10", right? The middle of 5'9.5" to 5'10.5". Totally, yeah. So 5 feet, which gets the one little prime there, 10 inches. And this is what's called a unimodal distribution. There is one mode that is occurring the most, not more than one. On the other hand, it is certainly possible to have a bimodal distribution where you have kind of 2 peaks. And an example of this would actually be the height of the entire US population. And I'm going to draw it more like what I would actually draw. So if I was drawing something like this, you'd probably have something that looked more like that, where over here you have a peak around 5'4" inches, I'm going to say, which is the average height of women, approximately. I'm making up numbers. I don't know if that's exactly true. I know it's close to true. And then you have another peak over here around 5'10" inches for men. So this would be a bimodal distribution. There are 2 modes that are kind of the most. They don't have to be the same height. Right? You can have a bimodal distribution that looks more like this, right? Where you have a peak here and a peak here. That's still considered bimodal because there's something of a most here and a most here. Yeah. So mode is just the thing that occurs the most. It's sometimes a good measure of the middle of a distribution, but not always. It's the least likely to always be a good measure of the middle. So again, so the mean, also known as the average, or sometimes it's even called the weighted average. It's called that because it gives more weight to the things that occur more frequently. So for example, that's a good example here. Actually, GPA is a really good example of a weighted average, right? The more A's you have, the closer your GPA is going to be to an A. So for example, let's say you had the following grades for, I'm going to make up just a lot. Like, let's say you had 4 A's, 2 B's, 1 C. Let's stop that. Let's pretend that that's there. All right. So what's my GPA? Well, as I'm sure you're all aware, an A counts for 4 grade point average points, a B counts for 3, a C counts for 2. We're not going to deal with pluses and minuses at the moment. So I would add up all of the A's. So I'd have, and let's make it 5 A's actually, just because I want this to be. So I'd have a 4 plus a 4 plus a 4 plus a 4 plus a 4. And then I'd have 2 B's, which are each worth 3 grade points, and then 1 C, which is worth 2. And I would divide that by the total number of grades I had, which is 8. And that would give me, let's see. So here's what I would really have done. I wouldn't have written 4 plus 4 5 times. I would have written 5 times 4 plus 2 times 3 plus 1 times 2, which is going to give me 20 plus 6 plus 2, so 28 divided by 8, which is 14 divided by 4, which is 7 divided by 2, which is 3.5. I feel like I might have made a mistake there. No, I didn't. So my GPA would be a 3.5, right? Those A's really pull me up. I guess you could view it that way, maybe. Yeah, that's not too bad. For this distribution of grades, I would say that the mode was A, right? A definitely occurs the most. I would say that the mean is, well, again, you have to go from letters to numbers. So I wouldn't say there's a meaningful mean, or sorry, a meaningful mean in terms of A's and B's. You'd say it's halfway between A and B. And then median. So actually really mean, I think most people probably have a pretty good idea of what it is. It's just the average. We've been calculating averages probably a good portion of our lives at this point. Median, on the other hand, is kind of funky. So median, there we go. So let's say you had some data measuring, let's say shoe size, because that's pretty easy to talk about. Shoe size, by the way, also bimodal in the same sort of way that height for men and women is bimodal. You've got kind of two little peaks for the kind of most popular shoe sizes for women and most popular shoe sizes for men. So let's say we had some very small data set. Like let's say we talked to some people and they had the following shoe sizes. Let's say I had some, let's say we're talking men's shoe sizes just because. So size 6, a couple 7s, some 8s. Let's not deal with half sizes, that's a pain in the butt. I have no idea what the average shoe size for a man is. I'm probably picking too many data points to make this easy. My brother wears a size 17, giant feet, seems like a real challenge. So let's say this is our data, and I want to find the median. So first of all, I have to count how many data points there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so n, the number of the size of our sample is 19. If your sample size is odd, then your median is going to occur right in the middle. So 19, the way you find it is it's at n plus 1 divided by 2 if n is odd. So here it's going to be at 19 plus 1 over 2, which is 20 over 2, which is 10. So it's going to be at the 10th spot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there, at the 10th spot. That's our median. On the other hand, if we had one more giant-footed person, size 17, then if n is even, right, so now in this red example, n is 20, then you take the average of the two middle spots. So you take the average of the 10th and the 11th spot, or more generally, the average of the n divided by 2 spot and the n plus 1 divided by 2 spot. Right, so n over 2, if n is 20, that's 10, and n plus, I'm smarter than this. Not n plus 1 over 2, sorry, n over 2 plus 1, which is 10 plus 1, which is 11. So that's the 10th and 11th spot. And then you have to take the average of those. So here, the median would be the average of 9 and 10, which is just 19 divided by 2, which is 9.5. Okay. So again, median, if you have an odd number of things, it's just the middle spot value. If you have an odd number, even number of things, it's the average of the two middle spot values. And as you can kind of see, as I was pointing out in the example before, or on her example, the median is very resistant to outliers affecting its value, right? This could have been a 17 or a size 170, which has a size 172. But if someone accidentally entered a really large value on mistake, it wouldn't really change the median at all. Whereas the average would definitely change a lot if you accidentally put in a really, really large shoe size with this small sample here. All right, so then Kimberly asked about, can you talk about range, variance, and standard deviation? Definitely. So, in fact, let's just stick with this example, even though it might be not fun to calculate. Well, actually, this is what we're going to talk about. So I'm still looking. I haven't really found a great online calculator, but well, actually, that's not true. I don't know if I have. So let's actually do this together. So I know I had something here. Where'd you go? I was looking at this one, but I didn't really know if it was any good or not because I'm kind of busy. So I was Googling around and I found one called Meta Calculator. I don't actually know anything about it. So let's look at it together. So I'm going to share my screen with you. You can also find it. It's literally just metacalculator.com or meta-calculator. But I'm going to share my screen again. Here we go. I have to click on share. Okay. So here is my place where I'm going to enter the data. So I'm just going to enter all these in real quick, which seems like it might be kind of a pain. So I can tab to the next one. So 6 and then 7, 7, 8, 8, 8, 8, 9, 9, 9, 10, 10, 10, 10. Whoops. And then I've got 11, 11, 12, 13, 17, 17. Whoops. Okay, so there's our data entered in. Let's close these things. I don't need those anymore. And then, was in the trash? Ah, yeah, in there. I might want them. So I'm going to click on basic statistics. Oh, let's see. So I think I'm on the basic statistics tab. And if I click on calculate statistics, look what I've got. So I've got the maximum value, which is 17. I've got the minimum, which is 6. The mid-range, I don't know what they mean by that exactly yet. Think about that. The mid-range, interesting, 11.5, that seems wrong. The sum of everything happens to up to 200. The count is 20. So the mean happens to be 10, which is just, if we add all that stuff together and then divide by 20, we get 10. The median, which we had already calculated, is 9.5. The mode is 8, and so this is technically a bimodal distribution because there are two values, namely 8 and 10, that occur the most amount of times, which is 4. We'll talk about the variance and standard deviation in a second. Is there no range on here? Oh, I remember what the mid-range is. Okay, yeah. So I feel like it's dumb that they don't actually have the range on here. That said, the range is super easy to calculate. It's just the, why do they call it mid-range? So I would say the range here is 11, personally, because it's 17 minus 6. But maybe they are doing something slightly different, and that's why they're calling 11.5 for the mid-range. To be honest, I don't know why they're saying that. I'll do some looking further to kind of figure that out. So let's go, and then we can talk about these things. Okay, sure. I'm going to stop sharing, but I might come back to this. So, pen, where'd you go, pen? Yeah. So the range, and now I could be making a small error here, and I will verify this later. But I would personally say the range is 17 minus 6, which is 11. There might be a reason that they're saying it's a little bit bigger, like maybe, no, I don't. I'll have to do more looking to really kind of figure out why. The variance is a measure of variability, not surprisingly, measure of how far the data is from the middle. So that's generally the idea of the variance. It's a measure of how much does this data set really differ from the middle. I mean, if you had a data set where everybody was a size 10, then the variance would be 0 because there would be no variation from the middle, which would also be 10. This is clearly not that set. So let me remind you, so the mean, the average, is one way of measuring the middle. And in this case, the average, I think they said it was, sorry, I'm looking at stuff here, the mean. All right, there's some weirdness here. I'm looking at the wrong, I'm looking at the wrong data. There we go. Apologies. The mean was 10, which you can totally find by doing this, right? So the mean would be add up all the shoe sizes. So 6 plus 2 times 7 plus 4 times 8 plus 3 times 9 plus 4 times 10 plus 2 times 11 plus 1 times 12 plus 1 times 13 plus 2 times 17. Divide that all by the total number of your sample size, which is 20, the total number of shoe sizes. And then if we do this, it should be 10. Well, let's actually double check. So this is 6 plus 14, which is 20. Now find 20 plus 32 plus 27 plus 40 plus 22 plus 12 plus 20, 13 is 25. 2 times 17 is 34. Add this all together. Let's see, we get 52, 72, 79, 119, 141. That seems wrong to me. This doesn't seem like that's 200 personally. Anyway, now I'm like, really? Did I make a mistake? No, it looks right. 12, 13. Yeah, that seems right to me. This is 52. This is 67. This is 47, 34, and then maybe I'm right. This adds up to, let's see, I have a calculator. Why am I doing this by hand? 52 plus 67 plus 47 plus 34. No, totally 200. I was just making some jump error before. So this is totally 200 divided by 20, which is exactly 10. So not surprisingly, right? The other thing we already did it for us. You normally probably shouldn't have to do a standard deviation, or sorry, an average, a mean by hand, right? Usually you should be using a calculator or something that's even like, you could totally do it with this as well. Sorry, with this calculator here, which I will show you guys how to do later. But for now, I might just use something like the meta calculator. It seems like it's pretty good. So that's our average. So the mean is 10. So let me ask you, Kimberly, do you want me to talk about how to calculate the variance? Okay. So calculating variance kind of sucks. Because what you're trying to do is you're trying to measure how far away everything is from the mean. So if you look at just data here, this number is 4 away. This number is 3 away. This number is 3 away. These are all 2 away. These are all 1 away. These are all 0. These are all 1, 2, 3. The issue here is that you can't just add up all the differences. Like if you did something like for variance, this is not the way we calculate variance, but an idea would be to say, okay, well, it's all the differences added together. 6 minus 10, plus 7 minus 10, plus 7 minus 10, plus all the way to 17 minus 10, right? If you added up all those differences, this would actually come out to be 0. And the reason why this comes out to be 0 is because all these first differences are negative, and all these last differences are positive, and they exactly cancel each other out. Because really you're just adding up all of these numbers, which we know adds up to 200, right? I was calculating the mean, it was 200 divided by 20. Subtracting all of the 10s, but if you subtract 10 and 20 times, you're also going to get 200. So you get 200 minus 200, which is 0. And that's definitely not a great way to measure it, because the variance should be something positive. You should measure how the stuff differs. So the idea here is that we want to make this easier to calculate. We don't want to use an absolute value, right? You could totally throw an absolute value around everything, and then everything would be positive. And that would certainly give us a nice measure of the difference from the mean, but the absolute value is a terrible function. It's not differentiable. There's other stuff that's just problematic with it. We don't love it. So instead, here is how you actually calculate the variance. It's all of the differences between your measurements and the average, and then you square those quantities and then you sum them. So the variance for this would look like the following. It would be 6 minus 10 squared plus 7 minus 10. I'm going to write it a little bit nicer. I'd have 7 minus 10 squared, but I'd have that twice because there's 2 7s. I'd have 8 minus 10 squared 4 times. I would have 9 minus 10 squared 3 times. I would have 10 minus 10 squared, which sounds dumb because that's just 0, 4 times. I would have 11 minus 10 squared 2 times. I would have 12 minus 10 squared 1 time. I'd have 13 minus 10 squared 1 time. And I have 17 minus 10 squared 1 time. Sorry, 2 times. Apologies. And the reason we are doing that is so that all of the values come out to be positive. So if we look at that, so 6 minus 10 is 4, negative 4 squared is 16. 2 times 7 minus 10 squared is 9, so 2 times 9. And then we get 4 times 8 minus 10 is negative 2 squared is 4. And then 3 times 9 minus 10 squared is 1. Plus 4 times 0. Plus 2 times 1. Plus 1 times 4. Plus 1 times 9. Plus 2 times 17 minus 10 is 49. Sorry, 17 minus 10 is 7 squared is 49. If you look, those size 17s are really, really contributing a lot to the variance, right? They are way far away from the mean, right? They're a whole 7 away from the mean as opposed to the size 6, which is only 4 from the mean. So they're really, the variance really gives a lot of weight to the measurements that are further and further away from the average. To calculate this, in fact, I can just look at the actual answer here. So looking back at the data here, well, that doesn't look right. So I'm looking back at the data we calculated, and unless I'm making some idiotic mistake in my brain, they said, oh, no. Sorry, I'm trying to remember if I'm forgetting something now. I don't think so. So they say the variance, that can't be right. Clearly, I'm forgetting something about how the variance works, which is unfortunate. Yeah, what am I forgetting? It's a good question. Let's take a look at the book. Sorry. So I should actually probably know this better than I do, but I don't. It's unfortunate. I know there's something I'm forgetting. It's probably that we need to divide by n, but I'm not positive. So yeah, let me double check here. I'm sorry, you guys. I usually know how to calculate stuff. Yeah, that's what I was forgetting. So you have to divide by the sample size. So adding this all up, let's use a calculator because I'm smart. So I'm going to get, let's see, what do we got here? 16 plus 18 plus 16 plus 3 plus 0 plus 2 plus 4 plus 9 plus 2 times 49. So that's equal to 166. But really the variance should be all of this divided by n, which is 20. So that's 166 divided by 20, which is 8.3, approximately. And my calculator, that's, hang on, that's interesting. Oh, no, that's right. Which is what they got when I saw the other thing. They got something else. I'm not going to worry too much about it at the moment. That's kind of the idea behind variance. And I'm going to do a little bit more double checking just to make sure I'm not doing something stupid here. I feel like I might be making a dumb mistake. But yeah, we'll double check on that. I will double check on that later. So the idea of variance, though, is that you're taking all these differences from the mean, squaring them so that they're all the same sign, so that they don't cancel each other out when you add them up, and then adding them up and dividing by the sample size so that you get some kind of meaningful measure of how far you are from how much, I hate to use the word variance to describe variance, but how much variation there is, or how much discrepancy there is between all of your data and the average. And then the standard deviation is just the square root of the variance. So once you know the variance of something, you know the, oh, sorry, I'm sorry, class was supposed to end 7 minutes ago. I apologize. I totally just got on a roll. So sorry. In the future, if you guys are aware that class is supposed to end at 11:50, please just let me know. I didn't mean to go over, but I kind of just got talking and went on and on and on and on and on. So I will just sum up by saying here, this is variance. I'm going to fix this. I'm going to figure out what's wrong with this calculation later, and then let you know exactly where the mistake I made was. And yeah, standard deviation is just the square root of variance. We'll talk more on Tuesday, which is when our next class is, but I really, really want to stress, if there are things you have questions about, yes, so the quiz will be due next Monday. I will post it up and I'll send out some instructions as well. But if there are things you have questions about statistics, like you want me to talk more about variance and standard deviation, you want me to do an example, you have a homework question, there's a question you wrote solutions to that aren't quite clear, I'm happy to do something, but you just have to ask for it. So send me an email, or even better yet, if you want to get some participation points, start a discussion thread, and I will happily make some videos for you guys. But really, really, the onus is on you all to ask me to do things, because otherwise I don't really know what you want to see. All right, I'm going to end the meeting. It's been great seeing you all. I'm also going to say next time, please, if you can, come with video on. My hair doesn't look great today. It's okay if your hair doesn't look great either. It's all right. All right. I'll see you guys next time. Bye.